The amplitude for this problem is given, and it stays constant throughout the closed line. So the amplitude is 0.075 meters. The frequency is given as 2 hertz. So the angular frequency, omega, is 2 pi times the frequency. And that will give us 2 pi times 2 hertz, which is per second, which gives us 12.6 radians per second. The period then is 1 over the frequency, so it's 1 over 2 hertz, or 0.5 seconds. And then we can say the wavelength lambda is the speed over the frequency, and we're given that the speed is 12 meters per second. The frequency we just found, or actually it's given as 2 per seconds, so we get a wavelength of 6 meters, and the wave number k is given by 2 pi over the wavelength, which is 2 pi radians over 6 meters, which is 1.05 radian per meter. We can find the wave number also by doing the equation omega over v. Omega is 12.6 radians per second. V is 12 meters per second, gives us 1.05 radians per meter. So either one works. All of that was part A. Part B is asking for the function, and for these kind of waves we know it depends on both position and time, and we can write this as A in general cosine 2 pi x over lambda minus t over the period. And if we plug in these values in, we get 0.075 meters cosine 2 pi times x over 6 meters minus t over 0.5 seconds, which we can simplify a little more and say this is 0.075 meters cosine. If we multiply the 2 pi times x and divide by 6, we get 1.05 radians per meter, which is, if you recall what k was, x minus 1 over 0.5 times 2 pi will give us 12.6 radians per second times t. So notice that this is the same as kx minus omega t. For part C, we're asked to find the function for displacement as a function of time when the position, so we want to find the y value when x is 3 meters and t is t. So that's plugging in the values. We get 0.075 meters times the cosine of 1.05 radians per meter times 3 meters minus 12.6 radians per second times t, which will give us 0.075 meters cosine of negative 12.6 radians per second t, which is the same as minus 0.075 meters cosine 12.6 radians per second times t. For part D, we're asked for the maximum power that this person produces, and we have the max power formula that says P max equals UF times omega squared A squared, where mu is the linear density for mass, F is the force, omega is the angular frequency, and A is the amplitude. So if we plug in the known values, we know that the linear mass density is given, which I just noticed is not given in the problem, but assume it's given as 0.25 kilograms per meter. The force applied is 36 newtons. Omega we found earlier to be 12.6 radians per second squared, and the amplitude was 0.075 meters squared. Doing all of this gives us a power of 2.66 watts. Continuing on to part E, what is the average power? The average power, one way we can find that is half of P max, which is 1/2 times 2.66 watts, which is 1.33 watts. And then we're asked at the final part, it says, as the person tires, the amplitude decreases. What is the average power when the amplitude is at a certain point? The new amplitude, so a bar, let's call it, if you look, 7.5 millimeters, which is the same as 0.0075 meters, which is the same as 1/10 the old amplitude. And so we can say that the new average power is going to be 1/10 squared, whatever the average power was, 1.33 watts. which is the same as 0.0133 watts, or 13.3 milliwatts.